Good morning, class. Here, you can see my uncleaned up face here. Okay, enough of that. Okay, so after the Zoom disaster yesterday in class, I will record that lecture again and get it posted for you. So I'm just going to redo the class for those that were present. Hopefully, maybe the presentation will get a little better. I don't know. We'll see. But so we started out. I had a question, an email question from a student related to this problem 248 that he was working through. And there is a mistake in one of the equations here. They actually come out with the right answer, I believe, at the end of it. I'm not sure if it was a typo or how, but anyway, he went through very carefully. And if you evaluate their equation, you don't get the answer that they post, but the answer they post is correct. So there's a sign error in the equation, and I'll talk through that pretty quickly here. This is a pretty good problem to study. It shows the energy balance, a couple different forms of work, and there's a heat transfer interaction. So this is pretty good. I like this problem, except for the minus sign mistake in one of the equations. Okay, so what we have an electric motor. And let me pull this up a little bit. There we go. Electric motor that's drawing 10 amps of current at 110 volts, as shown in the picture. The output shaft, or the output power or work from the shaft is 9.7, a torque of 9.7 Newton meters, and the rotational speed is 1,000 RPM. So this is pretty common as a way in thermodynamics problems to give you the output power from through a shaft, or input power as far as that goes. For operation at steady state, we want to determine for the motor the electric power required in kW, the power developed by the output shaft in kW, and the average surface temperature, TS, in degrees C if heat transfer occurs by convection to the surroundings at 21 degrees C. So, pretty good common sense problem. And, we know the motor is going to get hot. If you've ever been around an electric motor, next time you see one, put your hand on it briefly, make sure it's not too hot to touch. And, the motor is going to get hot. And so the electrical energy that comes in, some of it's going to be converted to heat and lost from the control volume of the motor, or I guess I should say the control mass, because we don't have any mass entering or exiting. We just have the mass of the motor here. So this would be a control mass problem, which is what we do in chapter 2. But some of that input electrical energy or work will be converted to heat and lost as heat transfer to the surroundings. And then the rest of it will be, in the steady state, the rest of it will be converted into shaft work and exit through the rotating shaft of the motor. And so the picture pretty well summarizes. We're showing Newton's law of cooling. Q dot is the rate of heat transfer, and that's H, a convection coefficient, times the area. And we're given the HA product to be 3.9 watts per degree Kelvin. And then the appropriate temperature difference, which here, now it's interesting. So the way they have written this, TF minus TS, so that's going to give a negative value, right? Because we know that the surface temperature of the motor is greater than the surrounding fluid temperature. It has to be, because the heat's being lost from the motor to the surroundings. So the way they've written that delta T, this Q dot is going to come up negative, because H can't be negative and area can't be negative. So the 3.9 has to be positive. And if they're going to get a minus sign out of, for Q dot, then you have to adjust the temperature difference so that it gives a negative sign, which TF, the 21, minus TS. TS will be greater than T1, so that will give a negative. And it's basically tied up in that where the sign error happens later in the problem. Okay, so let's move on down. So for the electric work that's done on the control volume, and since that's basically work done on the control volume, it has a negative sign attached to it, and that is appropriate. So you see the minus sign and then the voltage and the current. Now, I will make a comment here that electrical engineers would not really consider this correct. There actually is another factor here called a power factor that comes into play with an electric induction motor. And a power factor is a number between 0 and 1 that will be less than 1 unless you have an electric resistive load. So for an induction motor, that power factor might be a number like 0.8, 0.85, 0.9. But the authors in the thermal book don't want to get into power factor, so they just ignore it and assume it's 1. So we will assume it's 1, and that's fine. And I'm not, in this course, I'm not going to require you to learn anything about power factors, but I just throw that out there kind of for your information. Okay, so volts times amps in general is watts, and he wants to display this answer in terms of kW. So this would be minus 1100 watts, or if you divide by 1,000, you can convert from watts to kW. So we have minus 1.1 kW, and he's showing that's coming in. And the fact that it's coming in, by definition, makes it negative in terms of a sign. Okay. So then let's move on to the shaft work, the torque. And so this is work done by the control volume on the surroundings. And so this will be considered positive work, so we don't introduce a minus sign here. And the equation for shaft work, the rate of doing shaft work with torque is torque times angular velocity. But remember, as I'm sure you did in physics and probably dynamics and other things, this angular velocity needs to be in radians per second, not revolutions per second. So we have an opportunity to screw up here if we don't realize that and get our units correct. Okay, so the 9.7 Newton meters is the torque, and that's given. The 1,000 revolutions per minute is given. Sorry, got a phone call there. And so then we have to convert to radians per second. So there's 2 pi radians per revolution. And then we want that in radians per second. So we have to divide by 60. So you need to get used to that. That will probably show up in the future. And then that would give us Newton meters per second. And so there's 1,000 Newton meters per second per kW. And so this all converts out nicely to a positive 1.016 kW would be the rate of work being done by that shaft in the surroundings, in the environment. Okay, so that's all pretty straightforward. So let's go on to the steady state energy balance. And so the first law for a closed system is on a rate basis is dE dt, the rate of change of energy within the control volume with respect to time is equal to the net rate of heat transfer minus the net rate at which work is done by the control volume, okay? And that minus sign in that equation is part of the equation. It doesn't have to do with the sign on the individual work terms. So those have to also be considered in this. Okay, well, since dE dt is 0, you can bring the work term to the other side of the equation. And so you get the net rate of heat transfer is equal to the net rate of work for the control mass. And so we've got a work term for the electric energy coming in, and we've got a term for the shaft work or the torque work going out. So when we add those together, and we have to include their respective signs. So we have a negative 1.1 kW on the electrical energy and a positive 1.016 on the shaft work. And so when you add those together, we get the rate of heat transfer is equal to the net work, and that's minus 0.084 kW. And we know that the heat transfer has to be negative because the motor is hot and the surroundings are cool, and so the heat is leaving the control mass, and so it has to have a minus sign. So that is correct. Okay, so the mistake is then in that last equation before the answer. And so I'm going to go to some an Excel sheet that has these equations in here to kind of illustrate this maybe a little bit better. So this is Newton's law of cooling. And, in general, we usually think about writing this as positive. I mean, you can write it negative just as well. But, so when I look at this, I say, well, Q is going to be HA times T motor minus T air, because T motor is hotter than T air. And so this is all going to be positive, and this will give a positive number. But in our problem, because of the sign convention for heat transfer, I want this Q dot to be negative. Okay, so, and that's the number that we have, and there's our HA, which has to be positive, and there's the temperature of the air. So when I apply this Newton law of cooling for this problem, this is my heat transfer I've already calculated from the energy balance, and I went ahead and threw a conversion factor in because we're going to do this equation in watts instead of kW, so I'm going to just convert from kW to watts. And it's because I've got the unit watt in this 3.9 term. I could divide this by 1,000 and do it in kW. It would work just fine either way. And so then, since this is negative on the left-hand side of the equation, this is HA times, and I'm going to write the air temperature, which is low, and the motor temperature, which is high. So this bracket term, this delta T, will be negative times the 3.9 will, so I have a negative on both sides of the equation. That's what I'm saying. So that's correct. Then what they do in solving this is we simply take this equation and we solve it for T motor. Well, so what can I do? I can divide through by the 3.9, and it shows up under this, and then bring the T air term to the other side of the equation. So then when I do that, all three terms are going to be negative, right? Because the T motor stays over here, it's negative over here. The T air becomes negative when it comes to the other side of the equation, and the heat transfer, the 0.084, is already negative. That's the way we plugged it in. So there's a minus sign associated with this. And then, that's kind of obnoxious, so I can multiply through by -1 if I want to, or I can work it like that, either way. But so I get T motor, a plus T motor is equal to this plus heat transfer term plus T air. Now, when we go back to the solution here, right here, we see he's got this equation, he's got a plus here, and then he's got a minus here and a plus here. So he's got a sign error. So this should be plus. And then if you do that, then the math works, and you actually get 315.5 from the equation, which is 42.5 degrees C, which is an appropriate temperature for the motor. So his final answer is correct, but there is this sign error in here. This either has to be positive or the other two terms have to be negative as well. Of course, if you did, you get a negative temperature, so I guess you really wouldn't want to do that either. So this minus sign is incorrect. Okay, enough of that. Okay, so let's move on to chapter 3 here, and we're going to go partially through this. We've got chapter 3 has got a lot of stuff in it, so it's going to take a while to get through all of this. But learning outcomes, I'm going to skip over these. You can read these for yourself, but that's what you're supposed to learn as you go through chapter 3. So I'm going to move on through that. Okay, so first thing, we're still in the definitional part of the course. So we've got all this stuff we need to define. And so the first thing is a phase. Okay, and so a quantity of matter that is homogeneous throughout in both chemical composition and physical structure. So, the classic example is water. So you can think about water, it doesn't, you can have what, solid, liquid, or vapor. It's all H2O. And then to have a particular phase, a phase could be ice, the solid phase. It could be liquid, the water phase, or it could be, water vapor, which would be the gas or vapor phase. But so the term phase requires that it be all the same, it be homogeneous, the same, chemical composition, and that it all be liquid, it all be solid or ice, or it all be vapor. It can't be a combination of those. It can't be like a glass of ice water. That would not be one phase present. Okay, homogeneity in physical structure means that that the matter is all solid or all liquid or all vapor gas. So I've said that now twice at least. And examples would be the air we breathe is a gas phase consisting of a mixture of different gases. But if it's a homogeneous mixture, then it is still all in the gaseous phase, and it would be homogeneous in chemical composition if you have the same ratio with the number of molecules. So the air, even though it's a mixture, can still qualify. Drinking water with ice cubes. So you got liquid and ice, solid phase and liquid phase. So, you have two phases present. It's not a single phase, obviously. And another example would be vinegar and oil. Salad dressing contains two different liquid phases. And, it's hard to get that stuff to mix together. It really doesn't. You can shake it up, kind of make an emulsion out of it, but it never really combines into a single. So you're going to have those two different liquid phases present if you have olive oil and vinegar in the same container. Okay, pure substance, a substance that is uniform and invariable in chemical composition. And again, a great example is water. Or you could have ammonia, or you just have a single chemical species. Or if you have a mixture that it's perfectly, you assume perfect mixing, and so then it may have different molecules in there, but it's homogeneous throughout. It means that it doesn't change from one area to another. But it's chemical composition, and its chemical composition is, it must be the same in each phase as well. Okay, examples. Drinking water with ice cubes can be regarded as a pure substance because each phase, it's all H2O. So it has the same composition. They make an example of a fuel-air mixture in a cylinder of an automobile engine because it is well mixed. Now you have a variety of gases. You have some fuel, you've got air, so you've got oxygen, nitrogen, a little bit of argon, you've got a little bit of water vapor and all that. But if you assume it's completely and perfectly mixed, then it can be considered a pure substance until the spark plug goes off. And then you burn it, and then you've got, a mess of combustion products on your hands. Okay. The state principle for simple compressible systems. So this is kind of an arduous discussion here. I don't think it's anybody's favorite when they go through Thermo 1, but it's just something that you have to become a little bit knowledgeable about. So the state principle basically predicts how many independent properties we need in order to determine an equilibrium state. So any equilibrium state can have lots of different properties associated with it, and you don't have to know all of them in order to know everything about the state. For a simple compressible substance, we'll say, such as just water, we just need 2 independent properties. And then we can derive or determine all of the other properties that we might be interested in from those 2. And so, theoretically, at least, it's important to be able to predict for a given system. And more complex systems, you may have to think through and work through this state principle to determine, if I have a complex system with a lot of different fluids or materials involved, how many properties do I have to measure in order to fix an equilibrium state? So, for example, a mixture of in air, moist air, is considered a binary mixture of all the dry gases and water vapor. And so it turns out that we have to have 3 independent properties in order to determine a state, and then all the rest of the properties can be determined from those. So anyway, that's kind of where we're going in this. Systems of commonly encountered pure substances are called simple compressible systems. And we got a bunch of tables, so you should look in the appendix, and I may pull it up here in a few minutes on the screen, but if not, look in your book at all of these different appendices, A2 through 18, 22, and 23. The intensive state of a simple compressible system at equilibrium is described by its intensive properties. And remember, intensive properties are independent of the mass or the extent of the system. So my simple test is like if I had a piston cylinder and I divided it in half, or I had one that was half the size, but everything else was the same, what would the property change? So for example, the temperature wouldn't change, the pressure wouldn't change. Specific volume is volume per unit mass. So whereas volume itself is not intensive, volume per unit mass is intensive. Density is 1 over that, so it's intensive. Specific internal energy, which would be internal energy per unit mass, is intensive, and enthalpy is a slightly different energy term that we have not yet defined. But if it's specific, it is then energy per unit mass as well. It simply includes some other features that internal energy do not. Properties such as velocity and elevation are excluded because their values depend on arbitrary datum choices, such as 0 values at the surface of the Earth. For the state principle, these properties are not relevant. So we don't worry about the overall kinetic energy of the system, like if it's moving on a truck, or that if it's changing elevation from the bottom of the mountain to the top of the mountain. So those types of interactions are not included in the discussion about the state principle. Okay, not all of the relevant intensive properties are independent. And this is a big deal. We'll spend a lot of time talking about this today. Some are related to definitions. For example, density is 1 over specific volume, and specific enthalpy is internal energy plus P pressure times specific volume, and the PV is what we call a flow work term, and that comes into play when I have mass flowing into a liquid or a gas flowing into or exiting a control volume. The proper term, or the easier term, actually enthalpy is a convenience, because that term U plus PV will appear all the time in the equation. So after a while, the engineering community just said, well, those are all properties, U, P, and V. So if I combine those, that'll be another property. And it just makes life easier when we get to the control volume analysis. Others are related to expressions developed from experimental data. So, there are correlations and stuff out there that sometimes get used. Some intensive properties may be independent in a single phase, but become dependent when there is more than one phase present. And so the big example there, and we'll talk more about this, is, for example, if you're boiling water on the stove, the temperature at which it boils is dependent upon the atmospheric pressure in the room. So if you're at sea level and the pressure is 14.696 psia, or 1 atmosphere, then it boils at 212, 100 C or 212. But if I'm in Denver, Colorado, and the pressure is less, then the water doesn't boil at 100 C or 212. It boils at a temperature less than that because the pressure is less. If I was to put it into a pressure cooker or a piston cylinder and press down on it with not only the atmosphere, but the weight of the piston and the weight, you know, maybe I could maintain it at 100 PSI, pounds per square inch absolute. And then it boils, I believe the number is 327. So we can adjust the temperature at which the boiling occurs by adjusting the pressure at which that phase change happens. So you see, during that phase change, pressure and temperature are not independent properties. They are dependent upon each other. And so if you're boiling fluid on a stove, you can't fix a state with temperature and pressure because they're not independent. Okay. If you're just heating water, then yes, temperature and pressure are independent. If you're heating ice or you're heating a gas, they are, but if there's a phase change going on, then they're not. So we just have to be careful in how we select these independent properties, that the ones that we choose really are independent of each other. Okay, for a simple compressible system, values of any two independent intensive properties determine the values of all other intensive properties. And so that's what this state principle does for you. It tells you how many that you need. So this is the state principle for simple compressible systems, which is basically most of what we work on. Certainly, I think all of what we work on in Thermo 1 and Thermo 2, you do get psychometrics and moist air problems, which then will require that you have an additional property. So among alternative sets of two independent intensive properties, they kind of suggest T and V or P and V, and you stay away from T and P, temperature and pressure, because there are times when they're not independent, and so you could get into trouble with that. So we will soon show that temperature and pressure are not always an independent set, and I've already kind of talked through that, but we'll do a bunch more of it. Okay, so here is the PVT surface, pressure, specific volume, and temperature. And so it's a surface out there, and any point on that surface is an equilibrium point. And so you see you've got three coordinates. The way this is drawn, pressure is going vertically upward, and specific volume is going, heading towards the lower right-hand corner, in terms of increasing specific volumes and increasing temperatures, it's heading up towards the top right-hand corner. And so you can see that. So you can also think about looking at the sides of this to get a two-dimensional diagram. If you get down on the lower left corner and look up at it, you would see a pressure versus specific volume plot. And if you got down on the lower right-hand corner and looked up at it, you would see a pressure versus temperature plot. So anyway. So single phase regions on the surface include solid, liquid, and vapor. So you see we got solid over here, we got liquid over here, and we got vapors over here. And then we've got these two-phase regions in between. So say I've got solid here, vapor here, I've got a solid vapor region down through here. So I've got liquid over here, vapor over here, and so I have a transition from liquid over here to vapor, and this kind of shaded area is what's called the saturation dome or the vapor dome or some kind of dome. And that indicates the transition from liquid to vapor. As say, if you had water boiling on the stove, then you would start over here on this saturated liquid line and come across to at constant pressure to the saturated vapor line. We'll talk more about that. Okay, two-phase regions are located between single-phase regions. They're where two phases exist in equilibrium: liquid vapor, solid liquid. Okay, and so you can do a transformation. You can go from solid to a mixture to vapor, and you don't have to melt. So this transition from solid to vapor is called sublimation. And under the right conditions, a solid can just basically evaporate into a vapor. CO2, dry ice, I believe will do this. If you put it out on the counter, you see it, and it just basically from solid, it just disappears. It sublimates at atmospheric pressure. Kind of interesting. Okay, the dome-shaped region composed of the two-phase liquid vapor states is called the vapor dome. Mentioned that. So that's this area, and actually it reclines back into this temperature axis. So when we look at it straight on, it just looks like a dome that's vertical, but when you look at it three-dimensionally, it actually reclines back into this area. Okay, a state state at which a phase change begins or ends is called a saturation state. Lines bordering the vapor dome are called saturated liquid and saturated vapor lines. So the saturated liquid line starts right here and runs right, is that line up to the critical point. And the critical point is where the saturated liquid and saturated vapor lines meet. On this side, it's all saturated vapor from right down here. This is the triple point, and it goes up right up to the critical point. So right on those lines, on this line, you're all saturated vapor. On this line, you're all saturated liquid. At the top of the dome, where saturated liquid and saturated vapor lines meet, is the critical point, right up here on top. Critical temperature is the maximum temperature at which liquid and vapor phases can coexist. Above, at a temperature above that, we usually say it's just a fluid. And if you're at temperatures above that, there is no transition between liquid. It's not possible to have a liquid, so it's just all fluid type stuff. And the critical pressure, PC, is the pressure at the critical point. So right here on the pressure axis, that's the critical point, and that's the critical temperature, and that's the critical isotherm, which is a line of constant temperature, which passes through there. Okay, so now what I've done, I dug that diagram off the internet, but you're looking at this in terms of a two-dimensional PV diagram, looking at this face. So this is what you would see. The pressure on this axis, volume, and really this probably should be specific volume. I didn't quite tagged it right, sorry. But at any rate, so over here, where this is your saturated liquid line, it starts and it goes up to the critical point, and then your saturated vapor line is over here, and it comes up to the critical point. So right on those lines, you have either saturated liquid or saturated vapor. In between, we have a two-phase mixture of liquid and vapor. You know, if I'm over on this side, I'm mostly liquid. And then as I move across, and this is in terms of mass, the mass of liquid and the mass of vapor, here you're roughly 50-50, and here you're almost all vapor. These are lines of constant temperature. So on a PV diagram, you need to know how to draw an isotherm. And so basically, this represents the same temperature. And as I keep that temperature and pressure falls, say I've got in a piston cylinder and I allow the pressure to drop, then the volume will expand a little bit. And if I do it right, there may be some heat transfer involved, whatever it takes to maintain the temperature. As pressure drops, specific volume will increase a little bit, right? As I take pressure off the system, it grows a small amount. This is pretty small for most liquids until I get down here, in which case then I am at saturated liquid. If I if I add heat to the system, then I will start to vaporize it and at constant pressure. And so this would be a piston cylinder that maintains constant pressure, and the volume increases significantly as I boil away that fluid until I get over to the saturated vapor line. And then if I drop pressure from there and maintain temperature, then I will move out into this superheated vapor region. So that's T1. If I had a higher temperature, I can draw it like this. It's the same general shape. It crosses the vapor dome at a higher pressure, and it maintains its position above the lower temperature at T1. This diagram is indicating he's just going to call this a gas up here above the dome. That's fine. You can do that. A vapor, a gas. It's pretty much all the same. Liquid region over here. If I'm off to this side, I'm either what we call subcooled. So for example, if I'm at this pressure and I'm cooler than this temperature, then I would have to move this way because these are lower and lower temperatures as I come out here. I'm still liquid. So that means I'm cooler than the saturation temperature, which is this guy. So that means I'm subcooled relative to saturation. Or you can think about it as being compressed. If I'm out here, the pressure, so I've got an isotherm coming down here. Well, see, the pressure would have to get down here for that isotherm in order to be saturated. So I am compressed. I am at a higher pressure given that temperature. So you can define these states either by thinking about compressed liquid or subcooled liquid. It's really different sides of the same thing. Okay. All right, so we'll bounce back and forth here a little bit. Okay, so this one is looking at a diagram on that three-dimensional surface from the right-hand side, looking at, and you get a pressure temperature phase diagram, so we're looking at it over here up this direction, and then this PT is what we see. So we see something like this. So say it's interesting. This is the vapor dome, but you're looking at the side of it, and it goes into and out of the plane of the paper. So if that's the critical point in this plane, then as you do a transition, if we did a constant pressure, say we increased it up to this point, then at that point where you hit that liquid vapor line, you're going to come into or out of the plane, whichever way is positive, of the paper. As you come across the dome, I guess you would probably come towards us, increasing volume, and then once you got across it, then you could continue out into the vapor side. So there's a three-dimensional aspect to this, and you have to kind of think about it. Water, for example, expands upon freezing. That's why we have potholes in the road all the time in the wintertime when we get a bunch of cold weather, because the asphalt or the pavement will get little cracks in it, and the water gets in there, and then if it gets cold enough, it freezes. And when that water freezes, it expands, and then it basically pops the pavement loose, and then the cars run over it. And when the car runs over it, the rocks finally, the little pieces of pavement that have been broken up by the expansion, get knocked out of there, and pretty soon, you know, you go through some cycles of this and you got a nice pothole out there. So that's what happens. Now, other liquids contract upon freezing. And so you'll see these three-dimensional surfaces drawn for water, i.e. substances that expand upon freezing, and other substances. And there's a slight difference over around the solid liquid interface line, you know, just based on how the volume reacts upon freezing or melting. So water actually expands in volume upon melting, where, no, I take it back. Let's say it expands upon freezing, so it contracts. Water contracts upon melting. Most, lots of liquids go the other way. So, anyway. Okay, so saturation temperature designates the temperature at which the phase change takes place at a given pressure. And again, remember that there is movement into and out of the plane of the paper as those transitions occur, either from, you could be condensing the vapor to a liquid, or you could be boiling the liquid into a vapor, either way. Saturation pressure designates the pressure at which the phase change takes place at a given temperature. And see, these things for that phase change are not independent of each other. It's probably what, yeah. So within the two phase regions, pressure and temperature are not independent. So we have to emphasize that a bunch. Okay. So this is, in these slides, whoever put it together, this is their PV diagram. I thought it was a little bit measly, so I put that other one in. But at any rate, there's good information here. It shows, got a few other things tagged down at the bottom. This indicates the triple point, or the triple line, which means on that line we can have liquid, vapor, and solid all in equilibrium with each other. And so that's one of the defining physical points for a substance, a pure substance, water and others. You'll see, you can look up data for the triple point conditions, exactly what pressure, what temperature, and what range of specific volumes that is applicable for. Let's see, so we see the liquid vapor dome shaded in. We see lines of constant temperature. We see the critical, these are called isotherms. We see the critical isotherm comes down and just touches the critical point. It doesn't go into the dome. It simply touches and then sweeps on down this way. We see out here at higher temperatures, we get this nice smooth behavior. The ideal gas law would probably do a good job characterizing states along this line. Not so much over here, where you see this kind of bump caused by the presence of the liquid vapor dome. So ideal gas law without some correction is not probably very good for these vapor states out in here and maybe even up in here. Okay, so we'll talk more about that. There is a compressibility factor, a Z, that we define that helps us continue to work with the ideal gas law in areas, vapor areas fairly close to the saturation dome. Okay, so there is a TV, temperature versus specific volume diagram. And so note, on this diagram, we can put in isobars, lines of constant pressure. And so you see this would be the critical isobar because it is tangent to the critical point, just touches it, that one point. That's the only point it touches the dome, does not enter the dome. And so we see for water, it's 22.09 megapascals or 3204 pounds per square inch absolute pressure. So above that, at pressures above that, we cannot get to the saturation dome. Okay, and then so you see this would be atmospheric pressure, 14.7 or 1.014 bar. And so that's constant pressure all along there. If we take some water at sea level pressure and start to heat it, and we maintain that pressure and you heat it, it has to go up this line. At this point, it becomes saturated. If we continue to heat and maintain that constant pressure, we will start to boil the water. It boils all the way across until we get over here at G, which case I have 100% saturated vapor. And if I continue to heat, then I will start increasing temperature at constant pressure. If my process allows me to maintain a constant pressure. You have to have the right sort of apparatus for that in order to do the experiment. Okay. All right, so phase change. Let's consider a closed system consisting of a unit mass of liquid water at 20 degrees C contained within a piston cylinder assembly. Okay, and so let's see, we're down here, and so here's our liquid water. This pressure and whatever atmosphere maintains this constant pressure, in which case it's going to be 14.7 because he shows it on that line. Liquid at 20 degrees C, there we go. So we know that the temperature up here is 100 degrees C, or 212. So you see we are subcooled, or our pressure is higher than the saturation pressure. So this liquid is a compressed liquid. So we're over here in this compressed liquid, subcooled liquid region of the phase diagram. Okay. So that's represented by the blue dot, etc. And liquid states such as this, where temperature is lower than saturation temperature corresponding to the pressure of the state, are called compressed liquid states. Okay. And, you know, I think this is pretty much as far as I went in class. So I think I'm going to stop the lecture at this point. I'm going to pull up some of the tables here and we'll take a look because we did some of that in class as well. I think I have some open. Let's see. Yeah, this is the English unit version of this. I'll pull up the SI as well, but and I will email these out to you as well. So you want to have both of these. I mean, they're in your book. All thermal books have these tables, so you probably already have a copy. But anyway, so you get these, some of these atomic weights and critical properties of selected compounds. You got, I don't know, ammonia, argon, benzene, CO2, water down here at the bottom. So you get chemical formula, molecular weight, critical temperature. This is the US unit, imperial unit chart. So you get Rankine, critical pressure in atmospheres. And this is this critical compressibility factor that we haven't defined yet. You get into the table. And so, for example, let's see, if we go back. Let's go back. Yeah, this is pretty good. Let me blow this up a little bit. Okay, so we're going to start. This dot is 68 degrees Fahrenheit. And so if I come into, so this table A2, and E is for English units, and there's another one for metric, but we're 68 degrees, okay? And so now let's see, but this is a saturation table, so I gotta be careful here. I'm gonna get you all mixed up. So say at this point, I'm not on saturation, so that first table is only good for saturation saturated liquid, saturated vapor, and states in between. So when I go back to over here, so when I can't, if I go to 68 here, that would assume saturation. So see, I can't use this table, but this table is good for the saturation dome only. So I've got one that's keyed to temperature, and I probably should open, I'll open the one for the metric as well. It's this one. Okay, and so this is the metric table. And so it has the same thing. We have saturated water, liquid to vapor table, and this is keyed off temperature. So you get all of these round numbers in terms of temperature, and then it gives you the saturation pressure that corresponds to that temperature. So that water was 20 degrees C, and so the saturation pressure at 20 degrees C is 0.02339 bar, but atmospheric pressure is what, 1.014 bar. So see, we are at a much higher pressure than the saturation pressure, so we're in the compressed liquid region. Okay, so if I look down here, well, if I go down here far enough, these are superheat tables. I'll get to, you know, properties of compressed liquid water. So, you know, if I want to look up a property in compressed liquid, I have to come over here in this table, and I'm most likely going to wind up doing interpolations. So see, the lowest pressure I have is what, 25 bar, and there's 20 degrees C, and I have properties for that, but I'm only at 1.014 bar, so I'm way off of this. So I'm real close to saturation, but I'm not quite saturation. So anyway, let's go back to this for a second. So if I heat this up at this pressure, 1.014 bar, R14.7, if I heat it up to the dome, then I'll be saturated at 100 degrees C or 212. So I can go back to my tables. Let's go to this one. So let's see. So if I heat it to, say, 212, and there's my 14.7. So see, that's a common point. So that's a little out of the normal scheme of numbering, but they include it in the table. So at that point, then I am all saturated liquid, and I see that I have specific volume, I have internal energy, I have enthalpy, and I have entropy. Okay, and notice the big difference in specific volume. That liquid, you know, for a unit mass, this is a pound, doesn't take up much volume. If I vaporize it, it takes up a whole bunch. So it goes from 0.01672 cubic feet per pound to 26.8 cubic feet per pound. If you look in the metric, the SI table over here, let's go up. Where am I? Pressure. Let's get to the temperature table. Okay, so here is 100 degrees C. See, there's my saturation pressure, which is atmospheric pressure, 0.014. What I wanted to point it out is notice the units. This is times 10 to the third. So these numbers have been multiplied by 1,000. So really this number at 100, saturation at 100 degrees C is 0.0010435. So you have to move the decimal point 3 places to the left before you actually punch the number in your calculator. That's what this notation means. And it's because there's just so many zeros involved, they don't want to print all that stuff in the table, so they use this notation. We also get internal energy, enthalpy, and entropy. Internal energy we've talked about. We'll define enthalpy and entropy later in the course. Okay, so this is table A2. It is saturation states tied to temperature. So you can look up a round temperature and then you just get the saturation pressure that goes with it. Again, these are not independent. Given one, you can find the other. And then we have a pressure table, which, you know, if you're given a round pressure, you can maybe find it directly in the table, and it gives you the saturation temperature that goes with that pressure. So for example, at 5 bar, or say 10 bar, our saturation temperature is 179.9. And then you get all of the different properties at that temperature pressure combination. Okay, and so that's the end of the pressure table. And then we go into the superheat tables. So if you are superheated, then we can go back to the diagram real quick. Then you're going to be off in this region, and you're outside the dome on the vapor side. And so you can look up states out here. So we're given a pressure, we're given the saturation temperature, and we're given the saturation properties, that's of the saturated vapor. And then as we increase temperature at that same pressure, then we go on out, we're going up to 500 degrees C in this table. At least at this pressure, that probably changes as we go. But you got a different entry for different pressures. So this is 0.06 bar, which is 0.006 megapascals. It gives you both pressures. That helps you find it a little bit more. Or that would be 6 kilopascals. So anyway, you can go. So you got a whole bunch of this. As pressures are going up, you see temperatures are going up as well as the pressures get higher. Up to 900. Okay, so the highest one they include is 320 bar or 32 MPa. I guess that's 32,000 kPa. That's pretty high pressure. And then we have the compressed liquid water table that we talked about previously. And then we have a saturated water solid table. So this would be the solid to vapor information if you're doing sublimation type stuff. Okay. All right. I think that's probably enough for this lecture, and we will continue in class on Tuesday, and I'll get this posted and the link sent out to everybody. So I hope you all have a great rest of the day, and we'll see you guys on Tuesday. Hopefully Zoom will work.